So my name is Daniel Tiribaba. I'm PhD in epidemiology, and I'm from the Tennessee Clinical and Translational Science Institute at the UT HSC. Today we discuss about survival analysis. So the objectives of our today's presentation is to discuss survival, censoring, survival probability, median survival probability, X-year survival probability, survival curve, hazard, and hazard ratio. At the end of the presentation, the audience will understand censoring, survival probability, and hazard. So first, let's define what is survival analysis. Survival analysis is a statistical analysis which deals with the analysis of time to an event. So in survival analysis, we are interested in analyzing time to an event, like the probability of surviving up to a certain event. It is widely used in different fields. Survival analysis is called by different names in different fields. In medical science, it's called survival analysis. In engineering, it's called reliability theory or analysis. In economics or econometrics, it's called duration analysis. In sociology, it's called event history analysis. Given that survival analysis is the analysis of time to event data, so why don't we use linear regression? As you know, linear regression is a very popular method, especially for continuous data. So why don't we use linear regression given that time is a continuous kind of data? So the answer is that the survival time usually violates the assumptions of linear regression. In linear regression, there are certain assumptions that have to always hold for us to use linear regression. And one of the assumptions is that the outcome or the response variable has to be normally distributed, or the residuals of the outcome variable have to be normally distributed. That means it has to have a bell-shaped curve with no too many extreme values. And survival time may not be normally distributed. And in reality, survival time may not be normally distributed. Especially, we don't know about the survival time of the complete survival time of those who have been censored, those who have left the study without developing the condition of interest. So survival time might be bimodal. For example, many patients die immediately after surgery, but they may also die long after the surgery if they originally survived. Survival time might have exponential or other non-parametric distributions. So the survival time may not be normally distributed. It might have other distribution, other well-known distributions such as exponential distribution or non-parametric distribution. There are several non-parametric distributions. If you join a class in survival analysis, there are survival distribution such as Weibull distribution, log normal distribution, logarithmic distributions, exponential distribution, and the likes. So survival time might have non-normal distribution, such as exponential and other distribution that are listed, Weibull distribution and the likes. So those have different kind of parameters for the estimation of average survival times. Sometimes we are not able to observe the full extent of the survival time. I will discuss about censoring. So for example, when we start observing or follow-upping the participant for an event of interest, and say for example, the outcome is recurrence of a certain condition, health outcome. Some participants join the study, but they, without developing the condition in the middle of the follow-up, they leave the study. Either we lose their contact, they drop out, or probably they develop certain condition that preclude the first event of interest. And in that situation, we do not observe the full extent of the survival time. The participant might also complete or the subject might complete the study without developing the condition under condition of interest. Survival time is non-symmetric. We do not have negative survival time. So these conditions make linear regression inappropriate for the analysis of survival time. Non-normally distributed, the bimodal distribution, while in normally distributed data that can be analyzed by linear regression. In survival, we might have bimodal kind of distribution. And survival time may have different distribution than normal distribution. And we may not observe all the full extent of the survival time. And so there is the skewness and the likes. In survival analysis, censoring means there is incomplete survival data. Just like I explained in the previous slide, some participants leave the study without developing the outcome of interest. For example, the study might end before participants develop the condition or they drop out of the condition. So participants leave the study without developing the outcome under study. For human studies, the main reasons are loss to follow-up due to any reason, relocation and loss of contact with the participant or subject under study, or no outcome until the end of study, or participant dies due to other causes, or participant develops other conditions that preclude the first condition from happening. In those situations, we say the participant is censored, which means we have incomplete data about the participant. So a participant who left the study without developing the condition is said to be censored. So if you at any point, if you have a question, you can stop me.
Sure, Daniel, thank you.
So censoring in survival analysis. Censoring is classified into left censored, interval censored, and right censored. Left censored means the outcome has happened by the time the study starts. So the outcome has already happened at the beginning, and you don't want to include those in the analysis because the outcome has already happened. And this kind of situation, we say the participant is left censored. In another example, when the value of a given measurement is below certain detectable value, we say it is left censored. We don't know, we don't have complete data on the outcome that's measured. Interval censored is another type of censoring. The exact time of event is unknown, but it occurs between 2 time points. So when we follow up participant or subjects into the future, for example, the study follow-up is infrequently conducted, and say over maybe 4 or 5 years, you contact your participant maybe maybe at the end of the year or every few months. But say the outcome is, for example, the development of or incidence of type 2 diabetes. We don't know the exact time when the patient developed, but the patient developed the condition or the participant developed the condition between 2 time points, between the 2 follow-up times. In this case, we say there is interval censoring. So we don't know exactly when the condition happened, and the participant might also leave the study. And we never know when the participant left, but it's between 2 time points. So this occurs when the follow-up is infrequent. The other one is right censored. In this case, the participant leaves the study without developing the event. In this case, the participant in human studies, the participant might die. They in right censored survival time, the participant might die. The participant might develop certain condition and no longer can provide additional information about the condition or outcome under study. Or the participant leave the study at the end of the follow-up. This could occur before the end of the study or at the end of the study. So for example, if we assume this is a survival time and we have participant entering the study, let's say all of them enter the study at the time 0. So the first participant, for example, is censored between the time of 2 and 4, but we don't know the exact time. Probably this participant is in this study, the follow-up occurred at time 2, time 4, time 8, and time 10. So the participant at time 3, when we didn't follow up, might have developed the condition or might have left the study. Another person so left the study. The first one left the study without developing the condition. The other one developed the condition. And for both participant, there is incomplete information, and we say the one who developed the condition failed, and the one who left the study is interval censored. For the first participant, the participant left the study at time point 8, and at this moment when the follow-up was conducted, the participant left the study without developing the condition. The participant might also have died, might have lost contact and the likes. For the sixth participant, the participant left the study without developing the condition. The participant was alive at the end of follow-up, or the time point 10 when the last follow-up was conducted. And for the eighth participant, the participant developed the condition at the time point 8 when the third follow-up was conducted. So the study is carried over 10 years, and follow-up time happened at 2nd, 4, 8, and 10 years. And right censoring can happen during follow-up or at the end of follow-up, while interval censoring happens in between 2 follow-up times. So whenever we have interval censoring like this one, when we have incomplete information about the survival time for some of the participants, we usually do the analysis based on taking into consideration the interval censoring. When we don't have interval censoring and we have frequent follow-up and we know all information about the censoring time points and the failure time points, we use the regular kind of data analysis. Survival time is the time from the start of the study or observation to the time when the subject fails or experiences the condition of interest. So for example, the outcome might be cardiovascular health outcome, coronary artery disease, stroke, could be death, and many other health outcomes. It can also be treatment failure. So for example, we'll look at later on, like hip replacement might fail, joint replacement might fail, and the outcome in that case is failure of an outcome from occurring. a right sensor observation, it is unknown whether the subject would fail or no. So we never know whether at the end the subject will fail uh, due to the condition of interest, due to the exposure of interest. So the survival analysis answered what proportion of a population survives past a certain time point. And of those that survive, at what rate will they die or fail? And how do situations or characteristics increase or decrease the probability of a survival? So we can look at, based on the characteristics of participant, we can look at whether there is a survival difference. So some groups, some characteristics might increase the risk of failing, or they might promote the survival during the follow-up period. So we can analyze data to see what characteristics increases the risk of an event. So we don't really get into deep about the survival analysis. We don't get too technical, but we have few formulas such as this. So the survival time, survival at time t equals the probability of surviving t when t is greater than a given time point. So for example, when we follow up participant, say we are interested in the survival probability at the time, say at 6 months. What is the probability that participant survives 6 months? 6 months. And we can also say it's a probability of the probability that event hasn't happened by time t. And the probability of survival decreases as time increases. As we'll see using survival curve, the probability of surviving or survival decreases in most cases. At the beginning of the follow-up time, everyone is disease-free or alive. So we have 100% survival at the beginning or at the start of the study. If the event is days, if the study is long enough, everyone in the study will eventually die, like human beings. So survival curve is one of the graphical presentations of the survival analysis. On the x-axis, we have the survival time. It can be in days, it can be in years, in months, and the likes. On the y-axis, we have the survival probability. It ranges from 0% to 100%. So the survival starts at 100% and goes down as the follow-up time progresses. So in this hypothetical example, it's a survival curve for cancer metastasis by metarestine in mice. So metarestine is a recently discovered drug for the prevention of cancer metastasis and it's under development. So in the first studies, they administered metarestine, the drug, and so the drug is prepared in saline solutions, and it was administered to the mice or the subject under study. And the control group in the clinical trial, in the preclinical trial, the control mice group received the vehicle, or the vehicle in this case was saline solutions. So we compare the survival probability in terms of metastasis. When we say survival probability for metastasis, we mean how long can the mice groups under study stay without cancer metastasis. Metastasis mean cancer spreads into different body parts from the original primary site of development. So for example, if the cancer started in pancreas, and when metastasis occurs, it distributes elsewhere. So it enters to blood circulation and it gets into lung, brain, bone marrow, and the likes. So that's what we mean by metastasis. So we are looking at the probability of surviving metastasis, which means the mice stays, the cancer in the mice stays in the primary site and it does not spread to distant locations in the body. So we are comparing the drug and the vehicle or the control. And as you see, early on, there is not much difference, but from around the 30th days of follow-up, there is a significant difference between the two groups. So the meta-resting group have survival curve that's upper, which means for a given time point, the meta-resting group has higher survival time. So let's take, for example, the 60th time point. So when we come high here, the vehicle group has a survival probability of around close to 40%, while at the same time, the meta-resting group has close to 50% survival probability. So as time goes, survival probability decreases. At the start of the study, the survival probability is 100% or 1. And in this simulated data, the metastasis survival probability of in the vehicle or control saline injected mice is almost 0 at the end of the study, and about 40% in the meta-resting group. We can also present the survival curve with the number at risk at the bottom, as you can see. So the top one is the number at 6 at a given time in the meta-resting group. So at the beginning, we had 58 mice subjects under study at the beginning in the meta-resting group, and 42 in the vehicle or control group. As time goes, the number of subject at risk decreases as some of them already develop metastasis. So, or as they are removed from the study because of either they die of other condition or something like that. So we can also show the number of participants are at risk at specific times. And we have a p-value. This p-value is based on log-rank test. We can also use chi-square test and several other different tests for comparing the survival probability of the two groups. So when the p-value is less than 0.05, we say there is a significant difference in survival probability between the compared groups. X-year survival probability is one of the commonly reported survival data, summary data. When we say X years, we mean like 1 year survival probability, 2 years survival probability. For cancer, usually 5 years survival probability. So 1 year and 5 year survival probability are commonly reported for cancers. Survival probability at a given time point is calculated as 1 minus the number of those who fail during a time interval divided by the number of those alive at the beginning of the time interval. So at a given time point, we can calculate the survival probability as 1 minus the number of those who died or who developed the condition of interest at the time interval divided by the number of those alive at the beginning of the interval. Survival, so the cumulative survival to any time point is calculated as the product of the conditional survival probabilities of surviving each time interval. So for example, here we define the survival probability at a given time point, And the cumulative survival to that given time point is the product of all the individual survivals in a given intervals up to the time point that we are interested in. So the 5-year relative survival rate for pancreatic cancer is, for example, reported as for all SARE stage. SARE is Surveillance Epidemiology and End Result Registry. It's a registry for cancer from across the United States. It's reported from about 19 cancer registries, and it's representative of the country. And so for all stages of cancer, the survival probability, the 5-year survival probability for pancreatic cancer is about 9%. For those that have a distant metastasis, the spread of the cancer in different body site, the survival probability is very short. It's only 3% of the patients who have distant metastasis survive 5 years. And those who have only local expansion of the cancer and has no distal metastasis, the survival is a little better, about 12%. In localized pancreatic cancer, the 5-year relative survival rate for pancreatic cancer is about 37%. So this is data based on the people diagnosed between with the pancreatic cancer between 2009 and 2015, and it's taken from cancer.org. For colon, the survival probability is relatively better than the pancreatic cancer, as you all already know. So for all cell stage combined, all these combined, the 5-year survival probability for colon cancer is about 63%, which was 9 for pancreatic cancer. And distance is about 14%. That's also very low, but it's better than the pancreatic cancer, which was 3%. And about 71% can survive 5 years. Of those with regional colon cancer can survive 5 years. And about 90% of colon cancer patients can, with localized only primary tumor, can survive about 5 years. Again, the data is from the same source, cancer.org. So let's have a look at the survival probability for hip replacement. How long does a hip replacement last? So the 15 years survival probability of hip replacement is about 89%. About 20 years survival probability is about 70%. And the 25-year survival probability is about 58%. This data is based on 215,676 hip replacement is recorded in national joint replacement registries from Australia and Finland. Median survival is one of the very relevant and important survival statistics that is usually reported. So in survival analysis, we do not know the full extent of the survival time in those who have been right censored or interval censored. So we cannot calculate the mean survival time, as for some of the participants, the time to failure is unknown. So the median survival time is the most commonly reported statistics. And the median survival time is the survival time at which 50% of the participants or subjects under study have not failed yet. So it's not the middle time points when we arrange the survival time from the lowest to the highest, like other different kinds of data. The median survival time is actually the time at which 50% of the participants survive or have not failed yet. So for the meta-restin and vehicle drugs study, the hypothetical median survival time is for the meta-restin about 62.3 days, and for the vehicle it's 50.9 days, which means the meta-restin have longer median survival. And we have the 95% confidence interval. That means this is a point estimate for the median, and this is a interval within which the survival can be found if larger sample size have been taken. So it ranges between 57.8 to the upper 95% confidence interval is undetectable. It cannot be determined due to data. For the vehicle, the survival, the 95% median survival ranges between 49.3 and 68.1. So as you can see, the median is between these two values. Hazard ratio is another statistic that is commonly reported in survival analysis. It's one of the mainly reported actually. So hazard is an instantaneous risk at a next time unit given that the subject has survived up to a given time point t. So it's called an instantaneous risk, which means the risk at a given specific time point. It's not a risk or hazard during certain period. It's a given at a given time point. So conditional on the fact that the patient has or the subject has survived up to the first interval of that time point. So the hazard at time t can be represented by lambda t, and the hazard ratio, the ratio of the hazards in compared groups. And the hazard ratio can be represented by lambda in group 1 or the exposed group usually at time t divided by the lambda or the hazard in group 2 at time t. The hazard ratio is different from relative risk, which is a similar measure of association, in that the relative risk is a cumulative risk, which means the risk of some events happening over an extended duration, while the hazard ratio is an instantaneous risk. Hazard ratio is similar to incidence rate or incidence rate density or incident rate ratio. So the incident rate ratio or incident density ratio takes time percent into account. It uses the time percent or time year, for example, how many people will survive for this given number of years, and as a denominator. So that is similar with the hazard ratio, and the incident rate ratio or incident density ratio that's calculated for a study can provide about the same effect size at the hazard ratio. Hazard ratio is the ratio of hazard in those exposed or treated to compared to the hazard of the control group. For the meta-restin study that we mentioned in the previous slides, that was used for prevention of cancer metastasis. The hazard ratio of metastasis for mice that received meta-restin compared to the vehicle injector was 0.55, and the 95% confidence interval ranges between 0.28 and 0.89. The risk of metastasis was reduced by 50%, which means 1 minus the hazard ratio, 0.5 here, and times 100%, and gives us the percent by which the risk was reduced by metarrestin.
So can I ask a question?
Yes, go ahead.
What is the benefit? How do we read the confidence interval here? Like, how does it tell us that this is a good result or a bad result?
Yeah, very interesting question. Yeah, so that's very important. As you see in this case, for example, it ranges from 0.28 and 0.89. Uh, the null value for hazard ratio, for relative risk, odds ratio, and the likes, other measures of association, the null value is 1. What do we mean by that? We are saying we are comparing hazard in the two compared groups, and if they are equal, that means for example, the meta-restin, in the case of the meta-restin, if the risk of metastasis or the spread of the cancer to other organs and tissues was equal in both those treated by the drug under studies and those who are controlled, who are just given just fluid. If the risk is equal, the hazard ratio becomes 1. That means 1 means there is no difference between the two groups and the drug is not useful. When, for example, the drug under study reduces the risk, the hazard ratio becomes less than 1. As you see here, it's 0.50, which is less than 1. And the 95% confidence interval does not include 1. If it includes 1, it means 1 is a likely hazard ratio if larger sample size was taken into study, or if other samples from the same population were taken and studied. 1 could be a likely hazard ratio that can be calculated. So in this case, it doesn't include 1, which means this result is statistically significant.
Right. Okay, thank you.
You're welcome. So for example, sometimes we report with p-value, but also without p-value, it informs you. So we know that this result is significant because it doesn't include the null value or the value of equality, which is 1 for hazard ratio and ratios. The risk of metastasis was reduced by 50% based on this calculation. And you can calculate this kind of to tell how much the risk was reduced, by how much percent the risk was reduced or increased. You can, so for example, if in a state the hazard ratio was 1.7, and then when we calculate this, 1 minus 1.7, which means we have about 70% increased risk in those exposed. Cumulative hazard is one of the statistics that's also reported in survival analysis. The cumulative hazard is the expected total number of times each subject will experience the condition or event under study by time t if the events were repeatable. So for example, if the event is hospitalization, if the event can relapse and the participant can get it multiple times, how many times can a patient or participant develop the condition or during the follow-up time up to a given time point? So if the event is days in a state or something that does not occur again, cumulative hazard is not helpful for the purpose of interpretation. So for the meta-restin and the vehicle drug or the control drug, the cumulative hazard is displayed here. So it's related with the survival time and the survival probability, and hazard ratio is an increasing, mostly it's an increasing kind of function. So you start from low hazard at the beginning of the study, and the hazard goes up. The hazard goes up in cumulative hazard. And cumulative hazard can be greater than 1. We said the maximum for survival probability is either 1, which is maximum, or 100%. When we like multiply 1 by 100 and get a percentile. The cumulative hazard can be above 1, and that tells the number of times the event can happen through the subject under study, given that the subject has survived up to a given time point. So comparing the metarrestin and the vehicle drug has high risk of metastasis, while those treated by metarrestin have lower metastasis. We can also display the number at risk throughout the time points. Again, this is another example of cumulative hazard rate. This is the cumulative hazard rate of recurrent cardiovascular disease according to the stages of cardiovascular autonomic neuropathy in patients with type 2 diabetes. So the normal, early, and definite are the autonomic neuropathy states, cardiovascular autonomic neuropathy states. So these are calculated based on the heartbeat. There is a procedure called Valsalva maneuver where you tell a person to hold their nose and breathe through mouth, and the heartbeat kind of decreases, especially if you have tachycardia or fast heartbeat. If you hold your nose for a while and breathe through mouth, the pulse rate decreases. And so based on that, and also the heart rate between expiration and inhalation and expiration, and other different methods, the cardiovascular autonomic neuropathy states are calculated. And there is a normal, early, and definite autonomic neuropathy scales or scores. So this is a cumulative hazard of recurrent cardiovascular disease according to the stage of those cardiovascular autonomic neuropathy in patients. And it's again a cumulative hazard rate. It begins from 0 and goes. It can be above 1, like we said. Here is another. Again, this is from a study that is published by some group. Hohenloser as and colleagues in 2013. It was published in European Heart Journal, a very prestigious journal. So in this case, they are comparing the cumulative hazard between aspirin and apixaban for the cumulative hazard of stroke hospitalizations. So in those who received the 2 drugs. So as you see, the aspirin has higher cumulative hazard. That means there is increased risk of stroke-related hospitalizations as compared to the apixaban. And we have another example of cumulative hazard. In this case, the cumulative hazard is estimated and displayed for incidence cardiovascular disease for comparing the GG, CG, and CC genotypes of the single nucleotide polymorphism with the reference R1333049. This was published again in a very prestigious journal. So in this study, they found that the CC genotype had the highest risk, and the GG genotype had the lowest, and the GC genotype had a middle risk of incident CVD or cardiovascular disease. So generally, this was a presentation on survival. If you have any question.
Thank you so much. This was really helpful.
You're welcome.
Thank you, Daniel.
You're welcome. So we'll post this on our YouTube channel, or the YouTube channel of our department, the Tennessee Clinical and Translational Institute. If you want to collaborate on something, or you have a research question, you want assistance, we provide a bird clinic support. So if you go to the UTHSC TNCTSI, we have bird clinic support. I don't know. Let me share this slide. Let me share. So we have the bird clinic services where you can schedule a consultation with faculties and biostatisticians. And so this takes you to a website where you schedule a consultation. So for example, we are at the 66 North Pauline Street. When you click this, it takes you to the schedule of faculties, and you see the time when they are available. You click on the time point that suits you, and from here you can sign up for bird clinic consultations.
Yeah, thank you so much. This is, yeah, we work with like population level data. We